Good morning. I just posted the link. I'm like running a few minutes behind this morning. I'm sorry about that. So I'll give just a couple more minutes for folks to show up. But today we're going to talk more about series. This will be our second day talking about infinite series. I'm going to go back through the definition of an infinite series, what it means for a series to converge. And then I'll show you our first few little theorems. It's an exciting day. Let me switch to this. Yeah. Okay. Yeah, unfortunate notation, but that's where we left off last time. So then geometric series would be next. Not these theorems. Telescoping series, TFD, rules for sums. Okay. All right, looks like most folks are in now, so I will go ahead. Oh, yeah, Dalton, if you want to show me the shirt, I might be able to help you. But let's jump in to this stuff. So this is, of course, Cop 2. Today is the 8th. And today we'll be talking about series for some time. Pretty much all of chapter 11, besides what we've already covered, is series. And we are going to cover all of chapter 11. When we finish with section 11 point, I think it's 11.8, we will be ready for the test. Yeah, so actually 11.7, we'll be ready for test 2 after we finish 11.7, maybe a little bit of 11.8. So that's where we're going. Again, the test 2 is most likely going to be the week of the 20th, so 2 weeks. Specifically today, I want to remind you, we're in section 11.2, which is intro to series. The summation notation we talked about last time. So I'll just remind you the definition. The series sigma n equals 1 to infinity an, which is a1 plus a2 plus a3 plus and so on forever, is defined as the limit of partial sums so S sub capital N is the sum from little n equals 1 to capital N of a little n. Thank you, baby. So S1 is A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3, and in general, Sn is A1 plus A2 plus A3 all the way out to An. Right. It's defined as the limit of these. So the full series, sigma n from 1 to infinity, an, is the limit as capital N goes to infinity of sigma n from 1 to capital N of a little n. Another way to write that is you can just say limit n to infinity s sub capital N. because this thing right here is Sn. So S sub capital N is actually a sequence, right? You give me a number, capital N, and I can tell you what S sub that number is. So if, all right, here, if lim capital N to infinity S sub N exists and is finite, then we say that the full infinite series sigma 1 from infinity an is convergent, having the value of this limit another word we use for the value of a series is the word sum equal to this limit. Otherwise, we say that the series diverges. You going to the gym? Give me just 1 second, guys. It'll be all right. Okay, so the series is very much like a type 1 improper integral. Think of integral from 1 to infinity of f of x as being the same thing as the sum from 1 to infinity of an. In other words, series are integrals of sequences. That's the nice way to think of it. And just like the improper integral from 1 to infinity is defined as a limit of a finite integral, 1 to n, so too the full infinite series, the sum from 1 to infinity, is defined as the limit of the finite sum from 1 to capital N. And then this finite sum from 1 to capital N is what we call Sn, the partial sum. If this sequence Sn is convergent, then the series sigma an is convergent. So that's kind of a tricky thing here, right? You start off with a sequence an and you say, I want to add up all those terms. Then in order to do that, because that is an infinite process, you have to define the infinite addition problem here in terms of a limit of a finite addition problem. Each of these finite addition problems is just a number, so that in turn defines the sequence Sn. If the sequence Sn is convergent, i.e. if that limit exists and is finite, then we say the series sigma an from 1 to infinity converges. If that sequence Sn diverges, i.e. this limit is either not finite or does not exist, then we say that the series diverges. It's going to take some time for you to wrap your head around the relationship between the A's and the S's, and you must do this. All right, that is the key to 11.2. It is the key to your homework this week, and it's also the key to understanding pretty much all the shit we're gonna do after it. So my goal for today is twofold. First, to make sure you're really comfy with this sigma notation and the definition here of an infinite series. And then second, to introduce the first few little theorems connecting the infinite series to the sequences. So let's work through some little examples. Suppose the series sigma n from 1 to infinity an has partial sums Sn equal 1 minus 3 times 1/2 to the n. What can be said about the convergence of the series? Can anybody help me out with this? So I promise no advanced knowledge required here. We just have to think about the definitions. What do we know about convergence of this series? What do we know about this series period? Is there anything we know about this series? Well, we have a formula for the nth partial sum. So we know that the series sigma 1 to infinity an is defined to be the limit as capital N goes to infinity of the series of the little sum sigma 1 to capital N an. And what is this? This is Sn. So this is the limit as n goes to infinity of Sn. I have a formula for Sn. That's what they told us. That's the only thing they told us about this series. So if you have a formula for the nth partial sum, you can fuck with your series by taking the limit of that partial sum. Notice this is an Sn, not an An. That's a big deal. Sn and An are not the same thing at all. But now this guy, as capital N goes to infinity, 1/2 to the capital N goes to 0. So this is 1 minus 3 times 0, which is just 1. Plus the series sigma n from 1 to infinity an converges to the value 1. So think of the step from here to here as like finding the antiderivative in an improper integral. Finding the antiderivative in the improper integral is equivalent to finding a formula for the partial sum, Sn. That's the hard part. Here, they did the hard part for us. They gave us a formula for the partial sum. So there's a problem or two like this in your homework where I give you a formula for Sn and I ask you what's going on with the series sigma an. And just remember that the series sigma an is defined to be the limit of the partial sums, the limit of the Sns. That is the nice, easy way to go about this. Another problem type that you will encounter in your homework is just calculating partial sums. Let's say calculate the first 6 partial sums for the series. I'll call it S equals sigma n from 0 to infinity 1/3 to the n. How about that? And then guess as to whether the series S converges or diverges. All right, so here I've given the series a name. I'm calling it S so that I can refer back to it without having to rewrite this whole thing each time. I just want to call it S. That'll make my life a little bit easier. I want to calculate the first 6 partial sums for this series. Since my series starts at 0, the very first partial sum would be S0, which is 1/3 to the 0, which is 1. The next partial sum would be S1, which is 1/3 to the 0 plus 1/3 to the 1, or 1 plus 1/3. And if you have a common denominator there, you'll see that that is 4/3. My next partial sum, S2, is 1/3 to the 0 plus 1/3 to the 1 plus 1/3 to the 2, which is 1 plus 1/3 plus 1/9, which is 4/3 plus, what is this, plus 1/9, 4/3 plus 1/9, that's 3/3, 12, 13/9. That looks right. Thirds plus 1/9, 12/9. Yeah, 13/9. Good. S3 is 1/3 to the 0 plus 1/3 to the 1 plus 1/3 to the 2 plus 1/3 to the 3. So you see how I'm finding these S's? I'm just adding up the first few terms of this series. So Sn is the series that stops at the nth term. So S1 stops at 1/3 to the 1. S2 stops at 1/3 to the 2. S3 stops at 1/3 to the 3. So what is this? This is 1 plus 1/3 plus 1/9 plus 1/27, right? So this piece I know is 13/9 plus 1/27. I would multiply by 3/3 again, so that would be 39 40/27. I'll do one more. Let's say we'll just do the first 5. This is 1/3 to the 0 plus 1/3 to the 1 plus 1/3 to the 2 plus 1/3 to the 3 plus 1/3 to the 4, which is 1 plus 1/3 plus 1/9 plus 1/27 plus 1/81, which is 40/27 plus 1/81. And if we multiply by 3/3, that's 121/81. All right, so let's stop here. These numbers are the first few terms of the sequence of partial sums. Maybe if I write them as decimals, we'll be able to get a better feel for them. Let's try that. Here, do I have a, I'll use my, oh no, my phone is dead. So 4/3 is a decimal. Let's do it like this. It's 1.333. 13/9, 1.4444. 40/27, 1.481. 121/81. 1.49. So if you look at these numbers, 1, 1.3, 1.4, 1.48, 1.49. Do the S's appear to be getting closer and closer to something? Can we guess at the limit as capital N goes to infinity of S capital N? S0 is 1, S1 is 1.3 repeating, S2 is 1.4 repeating, S3 is 1.48, dot, dot, dot. S4 is 1.49, dot, dot, dot. So what do we think? What does the limit as capital N go to infinity of S sub capital N appear to be from this list? Is there a number that these guys are getting closer and closer to? .4, 1.48, 1.49. It looks to me like the limit as n goes to infinity of Sn is probably 1.5 or 3/2. i.e., it looks like my series, sigma n equals 0 to infinity 1/3 to the n, converges to 3/2. All right, that's the idea. You guys are being very quiet, which has me a little bit nervous. So let's come back here real quick. Do we understand where these calculations are coming from? Why S0 is what it is, why S1 is what it is? It's the first few sums of my series. So my full infinite series S, sigma n from 0 to infinity 1/3 to the n, that's 1/3 to the 0 plus 1/3 to the 1 plus 1/3 to the 2 plus 1/3 to the 3 plus 1/3 to the 4, on and on forever. That's the infinite series that I'm playing with. So the full series S is the sum of the powers of 1/3 going on forever. And what I'm trying to do is to get a feel for this by adding up just the first few terms at a time and see if, as I add more and more terms, is the sum getting closer and closer to something. So if I look at just the first term of that series, it's 1. If I look at just the first 2 terms of that series, it's 1.333. If I look at just the first 3 terms of that series, it's 1.444. If I look at just the first 4 terms of that series, it's 1.481. And if I keep going, it looks like as I add more and more terms to the series, the sum is getting closer and closer and closer to 1.5. In other words, the partial sums appear to be getting closer and closer and closer to 1.5, which would mean that this series converges to 1.5. All right, let me hear some thoughts. I'm getting a little nervous here. Something's muted. Is the chat dead? Nothing? Okay, okay. Yeah, it is kind of a recursive thing. Sn is actually a recursive sequence, yeah. Mm-hmm. It is. The catch here is that the addition problem goes on and on forever. So in order to figure out the infinite addition problem, we just let it grow little bits at a time and ask if that's getting us closer and closer and closer to something. Sn is the finite sum of the ANs. So Sn is the sum of the first n ANs. 20 part is a simplification of the S equation. Which equation, Nick? These guys? On chat. Sn is recursive. Yeah, you could say that Sn is recursive, but usually we won't be working directly with the Sns. Only in this first section will we be working with the Sns directly. But it is true that to get the next Sn, you always take the previous one and then add the next An to it, right? So the way I was doing these calculations, this 13/9, for example, I knew that this part added up to 4/3 because that was the previous guy. So I just took 4/3 and added 1/9 to it. And it is in that sense recursive, yeah. Now something you notice here, I never found a formula for S sub capital N, right? I never actually found a formula. I just looked at the first few terms and made a guess. So finding the formula for S sub N is generally a hard problem, generally a very hard problem. But there is one collection of series where we can always do that, and that is geometric series. So that's the next thing I would like to talk about with you guys. We're all comfy with this example. Everybody comfy with this example? No questions, doubts, concerns, curiosities? All right. Okay, let's do this then. So a geometric series is a series formed out of a geometric sequence. So something like S equals sigma n from 0 to infinity, a0 r to the n. These are geometric series, sums of geometric sequences. Yeah, absolutely, Simon. I will show you at least one example of thinking of series in terms of geometry. And there are some cool shapes, some nesting things, some fractalish things. All right, so this guy is called a geometric series. A0 is a constant, R is a constant, and they don't have to start at n equals 0. They could start at n equals 1, 2, or 3. But any series of this form, where you take a geometric sequence and you slap on a capital sigma, is called a geometric series. Theorem. Geometric series converge if and only if the absolute value of R is less than 1. If abs R is less than 1, then sigma n from 0 to infinity a naught r to the n converges to a naught over 1 minus r. So I'm going to prove this theorem to you. If r has absolute value greater than or equal to 1, then the series diverges. So I'm going to prove the theorem, and then I'm going to give you a slightly better formula for the sum of a geometric series. This formula works fine, but only for things that look exactly like this. And I'll give you a formula that works in more cases. But this is the easiest way to prove it. So this is how I will jump in. Let S be this series. Which is A naught plus A naught R plus A naught R squared plus A naught R cubed, and so on. Then Sn is the sum from 0 to capital N of A naught R to the little n. And this is A naught plus A naught R plus A naught R squared plus A naught R cubed. But this one does not go on forever. His second to last term looks like this, and his last term looks like that. Now what I'm going to do is factor out A naught, and what's left is 1 plus R squared plus R cubed. Now to R to the n minus 1, and then R to the n. And so this is the piece that I want to wrap my head around. To do that, I'm going to multiply both sides by 1 minus R. And I'll shuffle the A naught out front. And that gives me this. So I just take this equation, Sn equals A naught times 1 plus R squared out to R to the n. And I multiply it over here by 1 minus R and over here by 1 minus R. So I multiply both sides by 1 minus R. It's a sneaky trick. You might be wondering, why the hell would you do that? I'll show you. It makes something really nice happen. It's just a sneaky algebra trick. So this A naught will stay out front. And then what I'll have inside here, if I distribute the 1 to every term, then I just get 1 plus R squared plus R cubed all the way out to R to the n minus 1 plus R to the n. And then I'm going to distribute the minus R. So I distribute the 1 and I just get another copy of this thing. All right, 1 times this thing is this thing. And then this minus is this minus. And now I distribute the R. R times 1 is R. R times R is R squared. R times R squared is R cubed. And this is going to continue all the way up to R times R to the n minus 1 is R to the n. And then R times R to the n is R to the n plus 1. Now I distribute the negative and cancel any terms that cancel. The A naught is still out front. And then inside here, I've got 1 and then plus R minus R. Everybody see that? This 1 is this one. And then I've got a plus R here. And when I distribute this negative, I'll have a minus R. So the R's go. I'll have R squared minus R squared. Those will go. R cubed minus R cubed. Those will go. The term right before this one in the dot dot dots is R to the n minus 1. So I'll have R to the n minus 1 minus R to the n minus 1. Those will go. R to the n minus R to the n. Those will go. So the only things that don't cancel are the 1 and R to the n plus 1. Now divide through by 1 minus R. So Sn, if I divide both sides by 1 minus R, this will just go back to being Sn. And over here, I have A naught times 1 minus R to the n plus 1 over 1 minus R. So if the absolute value of r is less than 1, then lim n to infinity r to the n plus 1 is 0. Because that would be r to the infinity. And if r has absolute value less than 1, then you remember r to the n goes to 0. Therefore, lim n to infinity of Sn, it would be the lim as n goes to infinity of this. This piece will go to 0. So you get a naught times 1 minus 0 over 1 minus r, which is a naught over 1 minus r. And that's it. That's the proof. So if the absolute value of r is less than 1, then the nth partial sum, and we're able to find a nice formula for it here, has only this piece depending on n, and this piece goes to 0. So you end up with a naught over 1 minus r, just like we claimed we would. In particular, the series converges. Yeah, I'll just leave it like that. So you could say, in particular, if r is less than 1, then the limit as n goes to infinity of Sn is finite. So sigma n equals 0 to infinity a naught times r to the n converges. Converges and has sum, or has value, a naught over 1 minus r. So this is cool shit. We can use this on the example we did at first. So we can use this to revisit the sigma n from 0 to infinity 1/3 to the n. This is geometric. With r equal to 1/3. So the absolute value of r is the absolute value of 1/3, which is 1/3, which is less than 1. So the series converges. And has value a naught over 1 minus r. A naught here is 1, so this is 1 over 1 minus 1/3, which is 1 over, let's see, 3/3 minus 1/3, that's 2/3, which is indeed 3/2, as we suspected. So we were correct. Our guess earlier, based on computing those first few partial sums, was the correct guess. And now we have the tools to evaluate any geometric series. We have to identify the common ratio. If the common ratio has absolute value less than 1, then that series will be convergent. And the sum or value of the series comes from this formula, but only if your geometric series is already in this form. In particular, starting at 0, and not all of them do. So let me give you a better formula, or an easier to use formula for geometric series. So that was revisiting that example. All right. So if you have a geometric series and it goes to infinity, but you don't know where it starts, right? I mean, it could start wherever. Doesn't have to necessarily start at 0. I'll just leave the lower bound off to indicate that that this formula is independent of that. It's always the starting term over 1 minus the common ratio. This is only true if r has absolute value less than 1. If the absolute value of r is less than 1, then this series will converge no matter where you start, and its value will always be the starting term over 1 minus the common ratio. So for example, sigma n from 3 to infinity, 5 times 1/2 to the n. This is geometric because 5 times 1/2 to the n is a geometric sequence. So this series is a geometric series. And here the absolute value of r is the absolute value of 1/5 is 1/5, which is less than 1. So the series converges. And the value should be the starting term over 1 minus the common ratio. Well, what is the starting term? This is like 5 times 1/2 cubed plus 5 times 1/2 to the 4 plus 5 times 1/2 to the 5th, and so on. That's what this sigma notation expands as. And so according to my formula, that should be the starting term, which is 5 times 1/2 cubed over 1 minus the 1 minus the common ratio. I just realized I fucked up here. The common ratio is 1/2, not 1/5. Sorry. Yeah, 5 times 1/2 to the n. So r is 1/2. So that's 5 times 1/2 cubed over 1 minus 1/2, which is 5 times 1/8 over 1 minus 1/2 is still 1/2. So that would be 10/8, or I'll just write it as 10/8 first, yeah. And then if you divide top and bottom by 2, that's 5/4. So the 1 minus r formula, this works just fine as long as your geometric series starts at 0. But not every series starts at 0. Some of them start at 3 or at 10 or at 5. And so the easier formula for most folks to remember is you take the starting term, whatever the first term of the series is, starting term, and then you divide by 1 minus the common ratio. So the starting term over 1 minus the common ratio. And that'll work well no matter where your series starts. The book doesn't give you this formula. The book gives you the formula that I proved, but I've found this useful, so I thought you might find it useful. Questions on this example? So let me zoom out. You can see both of these examples at once to help you think about them. Yeah, there's a fair amount of memorization here. You know, formulas like this or rules like r needs to be less than 1 in absolute value. Those are things that we have to remember. The trick to remembering this shit, it's like learning a language, right? When you practice a new language, the trick So remembering your vocab and sentence structure and you know, conjugation, all that shit isn't to be like, I need to remember this, I need to remember this. It's to practice with it, right? It's to spend lots and lots of time practicing with it. So solving the homework problems is like minimal practice, but if you want more practice, you should go into the book and solve more problems from 11.2. Why is it the absolute value of R? Well, remember in our formula for the partial sum, the thing that makes this piece go to 0 is the absolute value of R being less than 1. So this piece going to 0 is what's necessary for this to have a finite limit. So remember when we talked about geometric sequences, we said the limit of R to the n will be 0 if the absolute value of R is less than 1. That's what's necessary in order for this guy to have a finite limit. So the series here will converge if and only if R to the n goes to 0, and the requirement for R to the n to go to 0 is the absolute value of R being less than 1. R is allowed to be negative, but it's the size of R. That's the idea. It's the size of R that determines whether or not this limit will be 0. And we want R to be small enough so that this limit is 0. So R is allowed to be negative. That's actually not a problem at all. But the absolute value of R is the size of R. And if R is too big, then this limit won't be 0. If R is small enough, then this limit will be 0. And it turns out that the exact requirement is for the absolute value of R to be less than 1. That is the if and only if for this limit to be 0. So that turns out to be the if and only if for this limit to be finite. There was another question or comment in the chat there. Right. Yeah, exactly. Morgan nailed it. It's not about whether R is to the left of 0 or to the right of 0. It's about how far away R is from 0. If R is very far away from 0, then R to the n, this piece, will get big. And we don't want this piece getting big. We want this piece getting small. If this piece gets small enough fast enough, then the series might converge. And it turns out that the precise restriction is that R is not allowed to be more than 1 away from 0. In fact, it needs to be within 1 of 0. It has to be small. So a few results on how to manipulate series algebraically, and then we'll have our very first convergence test for series. So theorem, rules for manipulating series. If sigma an and sigma bn are both convergent series, and here I'm writing sigma an and sigma bn without any bounds, but it's always understood that it goes up to infinity. So I'm just, it doesn't matter where the series begin, but if they are both convergent, then sigma of an plus bn is equal to sigma an plus sigma bn. You can change the plus to a minus. That works just fine also. Sigma an minus bn is the same as sigma an minus sigma bn. And sigma of a constant, c times an, the constant can pop out. That's the same as c times sigma an. In other words, the sigma operator is a linear operator. And if writing these without bounds scares you, you can always put in the n equals wherever 0 to infinity. But you should understand that this works just fine independent of these bounds. So while I'm putting in here n equals 0 to infinity, it would work fine if they were all n equals 1 to infinity or n equals 5 to infinity. It doesn't matter. If both the series sigma an and sigma bn are convergent, then you can split them up. You can split up the sum as the sum of the two series. You could split up this difference as a difference of the two series. And if there's a constant multiple inside, he can come out. An example of a place where we can use this is with the series sigma 1 to infinity, say 2 over 3 to the n plus 1 over 5 to the n. So just like you can split up integrals, you can split up series. In fact, the rules for splitting up series are the exact same rules as the rules for splitting up integrals. Play nice with addition, subtraction, and constant multiples. They do not play nice with multiplication or division. So first I could split it up like this. And then that first guy, I can pop the 2 out. And then what's left here are each geometric series. This is the same as 2 times sigma n from 1 to infinity 1/3 to the n, because 1/3 to the n is the same as 1 over 3 to the n, because 1 to the n is 1. And this other guy I can treat as sigma n from 1 to infinity 1/5 to the n. So each of these are geometric. This guy has, I'll call him R1 is 1/3. So the absolute value of R1 is the absolute value of 1/3 is 1/3, which is less than 1. So the first series converges. R2 is 1/5. So the absolute value of R2 is the absolute value of 1/5 is 1/5, which is less than 1. So the second series converges also. And overall, I'll take each one's starting term and divide by 1 minus his common ratio. So I'll have 2 times, the starting term here is 1/3, and the common ratio is 1/3. And then this guy has starting term 1/5 and common ratio 1/5. So that's the value of the series. And then we just have to clean this up a little bit. 1 minus 1/3 is 2/3. And here 1 minus 1/5 is 4/5. So this is 1/5 over 4/5. So what do we get all together? I can flip and multiply here. This will be 1/3 times 3 over 2. This piece here is all just 1. And then this piece, 1/5 divided by 4/5 is 1/4. So altogether we'll have 5/4. Oops, sorry, there we go. All right, so you can split series up. You can split them up over addition, and then the constant multiple here, that 2, can pop out, just like it would for an integral. And then I recognize that each of the things that's left is a geometric series. The first one has common ratio 1/3, whose absolute value is less than 1, so he is a convergent series. The second guy has common ratio 1/5. The absolute value of 1/5 is also less than 1, so that series is also convergent. And then finally, I can use my formula. This 2 comes along for the ride, just like it would for an integral. And then this series has starting term 1/3 to the 1, so that's the 1/3 upstairs, and then common ratio 1/3, so the downstairs is always 1 minus the common ratio. And I do the same thing for the other guy. Then I just simplify and add up. Okay. So you can manipulate series algebraically the same way you manipulate integrals. That's the take-home message here, and this example combines those facts with what we just learned about geometric series. I'll scooch this up, so if you're still writing, you can still see that. Okay. It is time, though, for something cool. So here's my question. Is there anything we can say for sure about the sequence AN if we happen to know that the series sigma AN, and again, if you want to include something like that there, you can. If you know that the series converges. Well, we know that the full infinite series looks like this. Right? Is the result of adding up infinitely many things. So if those things are not very, very small, then the series has no chance at converging. If you add together infinitely many things and they're not getting very, very small, then you're adding together a bunch of big shit, which is going to give you even bigger shit. And if you add together infinitely many big things, you're going to get infinity. So the result here is our first theorem on our first convergence test. And this is called the test for divergence. So you're going to have a bunch of convergence tests for series, right? We had one convergence test really for improper integrals. We had a few theorems that you could think of as convergence tests for sequences, but we're going to have a shitload of them for series, and you need to keep them organized in your brain. So this first one, test for divergence, says this: if the limit as n goes to infinity, little n, of the ANs, if that is not 0, then the series sigma AN automatically diverges. And again, you could include some bounds here, but you don't need to, right? You could say n equals 1 to infinity if you wanted to. But that's the result of this little discussion here. You're adding up a bunch of shit. So that shit better be really small. What do we mean by really small? We mean it better be going to 0. If it's not going to 0, then the series automatically diverges. This is called the test for divergence, and it's the easiest convergence test to use. Do not confuse this limit with the value of this series. So 2 notes. Lim n to infinity an is super duper not the same as sigma n from wherever to infinity of an. These are totally different. And that might seem super obvious to you right now, but down the line you might forget. You'd be surprised how often I see this. The other note here, the converse to the test for divergence is not true. That is, lim n to infinity of an being 0 does not guarantee that sigma an converges. All right. So theorem and 2 little comments. The theorem says, if the general term of your series, the things you're adding up, do not go to 0, then your series has to diverge because you're adding up too much big shit. The converse to that theorem is not true. If this limit is 0, that does not guarantee that the series converges. There are divergent series whose general term does go to 0. And then the other comment is just don't confuse these 2 objects. These objects are not the same thing at all. You'd be surprised how often I see someone write this series equals this limit. It's never true. It's never, ever, ever true. It's like saying that the integral of a function is equal to its horizontal asymptote, right? They're totally disconnected objects, nothing to do with each other. But you can learn about the series by studying the limit here. If this limit happens to not be 0, then you can stop and say, oh, this series diverges. That's it. Some examples of series on which you can apply this. Let's see, what does the test for divergence say?
Can we see the last page?
Sure. Yeah, here, I'll leave this for just a second. Oh, while you guys are writing, I'll grab some water. How about that? All right, so questions about the statement of the theorem here or how we use it? Okay then, so I am going to move to this. So I'll give you a few series, and I want you guys to tell me what that test, TFD, test for divergence, tells us about each of them. The first one I'll call S, and it can be sigma n from 1 to infinity, inverse tangent of n plus 1 over n, t can be the series sigma n from 1 to infinity sine of 1 over n. Q can be sigma n from 0 to infinity. How about e raised to the negative, let's see, I thought this was maybe 1 over n plus 1. And let's do one more. R equals sigma n from 1 to infinity natural log of n. Okay, so here's 4 series. I would like to see what I can learn about each of these series from the test for divergence, the test that we just wrote down. So in this first series, what is AN? AN is the stuff we're adding up. AN is the inverse tangent of n plus 1 over n. In the second series, AN is the sine of 1 over n. In the third series, AN is e to the negative 1 over n plus 1. And in the fourth series, AN is just the natural log of n. So in the series S, TFD, that's my abbreviation for test for divergence, says what? The limit as n goes to infinity of AN here is the limit as n goes to infinity of the inverse tangent of n plus 1 over n. What is that limit? What is this limit? You guys have been working hard on sequence homework, right? So we should be getting pretty good at these limits at infinity. What is the inside of arctangent here going to? What is the limit as n goes to infinity of n plus 1 over n? Okay, n plus 1 over n goes to 1 as n goes to infinity. So this is going to the inverse tangent of 1, which is pi over 4. And that's not equal to 0. Therefore, by TFD, the series S diverges. Because the limit as n goes to infinity of AN is not 0. Let's look at the series T. The limit as n goes to infinity of AN here is the limit as n goes to infinity of the sine of 1 over n. That's the sine of 0, which is 0. So what does TFD say about this guy? Here, the general term does go to 0, right? The limit of this guy is 0. I'm doing the same trick for the limit here as I did for the limit there. I just ask, what does the inside do? 1 over n, as n goes to infinity, goes to 0, and the sine of 0 is 0. So this limit is 0. Remember what TFD says. TFD says if the limit of the ANs is not 0, then the series diverges. But it doesn't say anything about the limit of AN being 0. So here, TFD is inconclusive. Right, we cannot conclude that the series converges. TFD says nothing if the limit of the ANs is 0. It just says if the limit is not 0, then the series automatically diverges. In the series Q, we have lim n to infinity AN is the limit as n goes to infinity e to the negative 1 over n plus 1. As n goes to infinity, this power goes to 0. So this is e to the 0, which is 1. And that's not 0. So here the ANs go to something other than 0. Thus, by TFD, Q diverges. So if the limit of the ANs is not 0, then the series diverges. If the limit of the ANs is 0, TFD is inconclusive. The last one here in R, the limit as n goes to infinity of AN is the limit as n goes to infinity of the natural log of n. That's infinity, which is again definitely not equal to 0. So R diverges by TFD. In other words, if I hand you a series and ask you, does this series converge or diverge? Your first thought should be, is that series geometric? If it is, use our theorem on geometric series. Your second thought should be, if the series isn't geometric, what does TFD say about the series? If I take the limit as n goes to infinity of AN, do I get 0 or not? If I don't get 0, then the series automatically diverges. If I do get 0, then TFD is inconclusive, and I have to move on to. So you guys were surprisingly silent as I did these limit calculations, which makes me a little bit nervous. I'd love to hear what your thoughts are on any parts of this. Oh, Sorry, yeah, chat is being funny today. I guess I'm not getting notifications. I see here you guys did respond things. Yeah. My bad. Normally I get this little yellow blinky thing on my chat window letting me know when you've typed something, but today I did not get anything. I see here, yeah. So most of these comments are good. How does it go to 1? So the inside of the arctan here goes to 1. If you want to see that, the details for this limit look like this. So I'm going to mess up my own notes here, but lim n to infinity inverse tan n plus 1 over n is equal to the, I shove the limit inside, lim n to infinity n plus 1 over n. And then like Fernando said, we renormalize. So this is lim n to infinity 1 plus 1 over n, which is the inverse tangent of 1, which is pi over 4. Yeah, I don't know why the chat is being weird today. My meeting controls are a little bit weird too. I think there was an update. So yeah, good. So since that limit is non-zero here, S diverges. Since the limit in the second guy, t, is 0, we get nothing, right? And then, this doesn't seem super complex, kind of a true-false checklist. Good, yeah. Yeah, Nicholas' observation is correct. So it's kind of like a checklist. The trick is to remember each result. Okay. Okay, I have one more example that I'd like to look at kind of like this, where we can use TFD, and then I'm going to show you about telescoping series, assuming time is good. Time is pretty good. So one more TFD example. Let's investigate the convergence of the series sigma n from 0 to infinity, -1 to the n. There's 3 different ways we could attack this now. We can jump in barehanded with the sequence of partial sums. S0 is 1. S1 is -1 to the 0 plus -1 to the 1, which is 1 minus 1, which is 0. S2 is -1 to the 0 plus -1 to the 1 plus -1 to the 2. That's +1. S3 is -1 to the 0 plus -1 to the 1 plus -1 to the 2 plus -1 to the 3. That's 0 again. So the sequence of partial sums appears to go 1, 0, 1, 0, 1, 0. Sn appears to be 0 if n is odd, and 1 if n is even. So the limit of the Sn's, which is S, this does not exist, because it just goes 0, 1, 0, 1, 0, 1, 0, 1. So there is no limit. They aren't settling down on any particular value as capital N goes off to infinity. Therefore, the series S diverges. Or by TFD. The limit as little n goes to infinity of a little n is the limit as little n goes to infinity of -1 to the little n. This is also DNE, which is different from existing and equaling 0. So S diverges by TFD. Or you could say that this is a geometric series. With the common ratio -1. The absolute value of R is then the absolute value of -1, which is 1, which is not smaller than 1. So S diverges according to our theorem on geometric series. So 3 different ways to think about this guy. TFD works great. TFD is nice and fast. I'm a fan of this solution. This is nice in that it gives you some insight as to why the series diverges. But if you just want to know whether or not the series converges or diverges, this does it really fast. So does the argument using geometric series. And you want to get comfy with all of these. Okay. The last thing I want to show you today are what are called telescoping series. You guys remember those old cartoons with the pirate and he's like sailing around on a boat and some guy up in the crow's nest on the top of the mast like has this long telescope and he's like, land ho, and then he collapses the telescope. It's one of those big long things that like slides into itself and collapses down. That sort of telescope is what we have in mind when we talk about telescoping series, because there are series where the terms collapse down. So the best way to get comfy with these is through examples. Let's just play around with the series S equals, we'll do the sum from 1 to infinity, 2 over n times n plus 1. Here, TFD is inconclusive. Because the lim as n goes to infinity of an is the lim as n goes to infinity of 2 over n times n plus 1. That's 2 over infinity. That is 0. So TFD is inconclusive. So a geometric sequence is a sequence which can be written as one constant times another constant to the n. A geometric series is a sum of a geometric sequence. So sigma, some constant times some other constant to the n. It's not necessarily that the rate of change is set, but that, yeah, there is a common ratio. So going from one term to the next, you're always multiplying by a fixed constant. That's what that means. We wanted to go back to this really quick. I can leave it here for just a second. And then we are going to talk about, I hope we have time to talk about telescoping series, or at least one example. All right, so remember, you can always watch the videos and complete your notes that way. I'll give just another maybe 10 seconds here. I suppose this should be a capital N, shouldn't it? Yeah. So if you attack directly with the partial sums, you're actually able to get a nice formula for the nth partial sum. It's this sequence that just goes 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. So that is not a convergent sequence. Therefore, that is not a convergent series, because the sequence of partial sums has no limit. Or by TFD, if you look at the limit of the ANs, that's also a DNE limit, which is not the same as being 0. So if the ANs don't go to 0, S diverges by TFD. Or as a geometric series, this has common ratio -1, which is not smaller than 1, right? The absolute value of -1 is 1, which is not strictly smaller than 1. So as a geometric series, we could say that this series diverges. All right, so we are going to move on. Telescoping series. Here, TFD doesn't help me. TFD is inconclusive because the limit of the ANs is 0. But what I can do PFD to AN, which is 2 over n times n plus 1, and try to write out Sn. So because the denominator here has 2 factors, and the gap between those factors is just 1, I have reason to believe that the PFD will give me something nice if I split this up. So I take 2 over n times n plus 1, and this is our second major use for partial fractions in this class. And I say I'm going to try to split it up like this. If I clear the denominators, I get 2 equals a times n plus 1 plus b times n. And at n equals 0, I get 2 equals a. At n equals -1, I get 2 equals b times -1. So b is -2. So my an, 2 over n times n plus 1, could be written as 2 over n minus 2 over n plus 1, which means my series could be rewritten as 2 over n minus 2 over n plus 1, like this. So now I start writing out the partial sums. S1 is 2 over 1 minus 2 over 2. S2 is 2 over 1 minus 2 over 2 plus 2 over 2 minus 2 over 3. S3 is 2 over 1 minus 2 over 2 plus 2 over 2 minus 2 over 3 plus 2 over 3 minus 2 over 4. And what you see is that there's actually going to be a lot of cancellation, right? This guy will cancel with this guy. This guy will cancel with this guy. And in general, if you try to write out Sn, that will be 2 over 1 minus 2 over 2 plus 2 over 2 minus 2 over 3 plus 2 over 3 minus 2 over 4 plus, and we'll write the last few terms here, 2 over n minus 1 minus 2 over n plus 2 over n minus 2 over n plus 1. And now look at all this cancellation. The 2 over 2's cancel. The 2 over 3's cancel. The 2 over n's cancel. Here, this minus 2 over 4, the very next term in here is plus 2 over 4. So he will cancel also. And if you ask yourself, what is the last term right before this one? It's 2 over n minus 2 minus 2 over n minus 1. So this guy will also cancel with the term immediately before. So Sn simplifies to 2 over 1 minus 2 over n plus 1. And this is that foot-a-dump cancellation that we call telescoping. Therefore, S, my full infinite series, is the limit as capital N goes to infinity in S sub capital N, which is the limit as capital N goes to infinity of 2 minus 2 over n plus 1, which is 2 minus 0, which is 2. So the series S equals sigma n from 1 to infinity 2 over n times n plus 1 converges to 2. And the way we got there was by running some partial fractions, splitting up my an into these two different pieces, and then noticing that there's a lot of cancellation when you write out these terms. We write out the first few partial sums to notice the cancellation pattern. Then you write out the full nth partial sum and see exactly what cancels and what survives. Here, only the very first term and the very last term don't cancel. And since that very last term goes to 0, the limit as capital N goes to infinity of S sub capital N is 2 minus 0. And then that limit is the definition of the full infinite series S. So this guy is equal to or converges to 2. Series where you get this nice cancellation are called telescoping series. They do not always involve partial fractions, but they often involve partial fractions. So I will give you some more practice with telescoping series next time, and we'll also talk about the integral test, which will be our second big convergence test. So I think that is probably about all we have time for today. Let's see, there was a question there in the chat. How do we know when to use this telescoping series? If your series is summing a rational sequence, that is, if your series kind of looks like this, especially if the factors of the denominator are close to each other, like the gap between n and n plus 1 is just 1, then you have a good cause to guess that the series will telescope, and you should try something like this. Otherwise, the only times the way you would recognize that a series telescopes is by writing out the first few partial sums and noticing that there's a shitload of cancellation. If there's a shitload of cancellation in the first few partial sums, there's probably a shitload of cancellation in the full partial sum, which means the series probably telescopes. So if your other convergence tests don't give you the info you want, or it looks like this, or you write out the first few partial sums and notice a lot of cancellation, then you should probably try and attack it from this telescoping series perspective. All right, that's why I'm going to stop the meeting for today. If you guys want to chat some more, you can come by my office hour. I'm going to be switching over to that real soon here. And it's not super hard stuff that we're doing in the sense that each little task is a task that you've tackled before. What is hard is keeping the logic straight in your head and getting comfortable with the words. So make sure you're spending time talking to people about this stuff. Watch videos. There's lots and lots of good videos. I'll try to remember to update our modules in Canvas today with some outside resources for y'all. But 3 Blue 1 Brown, Patrick JMT, MIT OpenCourseWare are all great sources for videos on infinite series that are pretty tractable. So I'm going to end this meeting. I'll pop open my office hours. I am going to grab a little bit of food, but then I will be in the office hour. So if you guys want to chat, I'll see you there. Otherwise, I'll see you on Friday. Remember to keep working on that homework. If you need more time on anything, submit an extension request. I'll go look at those today to make sure everything is clear. All right. See you guys Friday.